Determining the ship's stability is essential for its safe navigation. Ship stability calculations require ship officers to extract the values of hydrostatic parameters from the hydrostatic tables. These hydrostatic tables show draft in the first column on the left. Strictly speaking, the true mean draft and the midships draft are different. This difference matters with draft surveys to accurately calculate the quantity of cargo transfers. Here, we are just concerned with monitoring transfer operations on small ships. For our purposes, we will use the forward draft, at the draft mark, plus the aft draft, at the draft mark, divided by 2. The hydrostatic tables provide the ship's displacement for each mean draft. The displacement provided is usually based on the volume of seawater displaced by the underwater hull at that draft. If the ship is float in a freshwater river, the displacement would have to be adjusted for the density of freshwater. The displacements in the hydrostatic tables take into account the shape of the ship's hull. The third column, TPC, means tons per centimeter. It is the amount by which the displacement must be altered to change the draft by 1 centimeter. As weights are loaded and discharged, there is a change in draft that occurs with the change in displacement. The amount by which the true mean draft will change as the displacement changes is a function of hull form. It is determined by naval architects and tabulated in the hydrostatic tables. The TPCs in the hydrostatic tables also take into account the different water plane areas at different drafts. Let us consider what happens when a weight is loaded on the center line of the ship. For starters, a weight loaded on the center line will not create any port or starboard list on the ship. The added weight will cause an increase in draft, and possibly a change of trim. First, we assume the weight is loaded at the ship's longitudinal center of flotation. The draft of the vessel will change by an amount equal to the weight divided by the TPC, and this change can be considered uniform throughout the vessel's length. After loading the weight, the new draft at the longitudinal center of flotation, LCF, is calculated. Enter the hydrostatic tables and extract values of the LCF and the moment to change trim 1 centimeter, MCTC. The weight is considered to be on board, and now has to be shifted from the LCF to its new center of gravity. The change of trim after loading a weight, or several weights, can be calculated. The final drafts at the perpendiculars can also be calculated. Let's look at loading 500 tons on the center line of a big ship, 200 meters long. The initial drafts are 8.5 meters forward, and 9.5 meters aft, making the mean draft 9 meters. We go to the hydrostatic tables with the mean draft, 9 meters. We extract the TPC at this draft, 49 ton. The longitudinal center of flotation is 0.99 meters aft of midships. The moment to change trim by 1 centimeter is 728 ton-meters. The bodily sinkage is the added weight divided by the TPC at the draft. In this case, the 500 tons is divided by 49 tons TPC. The bodily sinkage, or change in draft, is 0.1 meters. Up to now, we've treated the weight as being on the center line and above the ship's longitudinal center of flotation. We've used TPC to find the change in draft. Let's look at calculating the change of trim. We will need to calculate the distance from the LCF to the weight's center of gravity. That distance is 0.99 plus 50 equal 50.99 meters. This distance is used to calculate the trimming moment. The trimming moment is 50.99 multiplied by the 500-ton weight added. The trimming moment is divided by the MCTC for the draft. That is 25,495 divided by 728 is equal to 35 centimeters. The change of trim will be by the head because the weight was loaded forward of the LCF. Let us calculate the change of the aft draft due to trim. First we must find the distance from the aft perpendicular to the longitudinal center of flotation. that is 99.01 meters. The change of the aft draft due to trim is 99.01 divided by 200, then multiplied by the total change of trim. So we have 99.01 divided by 200 then multiplied by 35. That gives us a change in aft draft of 17 centimeters. This change is a decrease in draft because the weight was loaded forward of the LCF. We already know the total change in trim is 35 centimeters, and the change of trim aft is 17 centimeters. The change of trim forward is 35 minus 17 equal 18 centimeters. The weight was loaded forward of the LCF, so the change is an increase in forward draft. To recap, note the original drafts, and calculate the mean draft. Use the mean draft to find the TPC in the hydrostatic tables. Use the TPC and the loaded weight to find the bodily sinkage. Use the mean draft to find the LCF and the MCTC in the hydrostatic tables. Use the LCF to find the trimming moment, and the MCTC to find total change of trim. Use the LCF again to apportion the change of trim to the forward and aft drafts. Let us consider the effect of loading weights off the center line of a ship. Let us first look at a weight being transversely by 5 meters. The transverse shift of an internal weight will create a list on the ship. On a ship with a displacement of 5,000 tons, and GM 0.3 meters, 20 tons was shifted transversely by 5 meters. Let us calculate the angle of list created by this cargo shift. The weight is 20 tons and the distance from the center line, after shifting, is 5 meters. The listing moment is 20 multiplied by 5, equal 100 ton-meters. We can find the tangent of the angle of list by dividing the listing moment by the product of the displacement and the GM. We can then use tables or a calculator to find the angle with that tangent. Let us now look at a ship with a list that we want to correct. The ship's clinometer shows she's listed 8 degrees to port. We are required to find how many tons must be transferred from port to starboard to upright the vessel. The transferred weight can be cargo, ballast, or maybe fuel. The vessel, that is listing 8 degrees to port, has displacement 12,000 tons, the km is 7.54 meters, and the kg is 6.8 meters. We are required to find how many tons of salt water ballast must be transferred from number 2 port double bottom tank to number 2 starboard double bottom tank, to make the vessel upright. The centers of gravity of the double bottom tanks are 10 meters apart. We can find the tangent of 8 degrees using tables or a scientific calculator. The listing moment is the product of the displacement multiplied by the GM, multiplied by the tangent of the angle of list. The distance moved by the weight is the distance between the centers of gravity of the tanks, 10 meters. The weight is 1248 divided by 10 equals 124.8 tons. To bring the vessel to upright, the listing moment caused on the port side must be the same as on the starboard side. So we have to transfer 124.8 tons of sea water to the starboard side of the double bottom tank to upright the vessel.